Welcome back to our channel Time Before Space, a channel where we explore the fascinating world around us through interesting videos, engaging interviews, and shorts. Let me ask you a question. Have you ever been in front of a mirror and noticed that your left side becomes your right side and vice versa? Mirrors are known to invert the left and the right positions of objects. But have you ever wondered why mirrors tend to invert only the left and the right positions and not the top and the bottom positions? Watch this video where great physicist Richard Feynman explains this question with great simplicity. Now let's add on to this and imagine something curious. Imagine that you're holding an egg in front of you and standing in front of a mirror. That's where something surprising happens. Surprisingly, the mirror has no effect on the egg. The image of the egg remains the same as the egg itself, with no apparent inversion. That raises an interesting question. Why do mirrors invert objects like us, humans, and not objects like eggs? This is because eggs are symmetric. And that brings us to our topic of discussion today, symmetries in physics. While the previous video on bounds in physics talked about how the nature limits us, in this video we talk about how the world of physics gives us a freedom of choice. Fair warning, this video will get progressively more advanced with each symmetry that we discuss today. So let's dive right in. The first symmetry on our list is the symmetry of translation. Just like the smooth movement of an ice skater sliding across an ice rink, translational symmetry of physics reveals that the laws of physics remain unchanged regardless of where you are. As long as you make sure that your frames of references where you make your observations of physics are inertial. In simple words, if different locations where you make your observations of nature cannot distinguish between different points of space, the fundamental principles governing the behavior of particles remain the same. No matter if you're observing the experiment from the comfort of your home or doing the experiment in a distant galaxy far, far away from here. The statement of translational invariance of physics not only applies to where you are in space, but also where you are in time. This is the reason why experiments conducted by Newton 400 years ago can still be tested and validated by us today. Isn't that amazing? My physicist and mathematician friends would be upset if I do not mention that these symmetries lead to conservation laws via the Noether's theorem. We would talk about them in a later video. Now let's give our discussion a little spin. Lift the object in front of you. Did you feel its weight? Well, you just made an observation in physics. You observed the force of gravity via the weight of the object. Now turn yourself. Do you still feel the force of gravity via the weight of the object? Yes, and it is the same in all directions. This is exactly what I'm talking about. The symmetry of rotation tells us that the laws of physics remain unchanged under rotations around any point. You turned around, and the laws of gravity still remain the same around you. Through the Noether's theorem, one finds out that this rotational symmetry leads to a conservation law known as the conservation of angular momentum. More on that in a later video. Now let's talk about another interesting symmetry. Have you ever wondered how the vast details of our planet Earth can be faithfully reproduced on small models known as globes? While making such objects, the enormous size of continents and oceans do shrink down to small, but the directions and the angles remain the same. This is how one can understand scaling transformations. Shrinking the details of this giant planet on a minuscule model of a globe is a change or a transformation, what we physicists call a conformal transformation. There's some theories in physics that do not change under these conformal transformations and are called scale invariant because it does not matter what scale you choose to describe your theory. It's important to note that these scales are not limited to scales of space and time. These scales could be any physical property like velocity, momentum, or even energy. For example, if a theory shows energy scale invariance, the predictions of that theory would not change regardless of whether you use that theory under low energies or even high energies. Scale symmetry reveals that the laws of physics remain the same under changes of scale, whether we explore the vast reaches of the cosmos or the infinitesimally small world of particles. Now, I would like to talk about two special symmetries in nature. These symmetries, although not so obvious in daily life, have far reaching consequences in the theories of physics that describe our universe. These symmetries are gauge symmetries and supersymmetry. Among other things, the word gauge means a measuring device. In simple words, gauge symmetry tells us that the mathematical measuring device that you use to describe a physical quantity in your theory cannot change the underlying physics. Let's take the example of electromagnetism, the theory that is enabling you to see me and me to see myself. It is the theory of light. In this case, the electromagnetic fields in the theory are described by a mathematical framework called the electromagnetic gauge theory. This framework includes the more familiar Maxwell equation. The gauge symmetry in the electromagnetic theory helps us to choose different gauges to represent the electromagnetic theory. But the physics, the underlying physics, would remain the same. And the choice of gauge would have no effect on the predictions that the theory makes. It's like looking at an artwork through different angles, and that doesn't change the artwork. In our case, the artwork is the part of physics that the theory describes, and the different angles that we use to view the artwork are the different gauges that the theory permits. This freedom of choice that the gauge symmetry gives us helps us to gain beautiful insights about the part of physics the theory explains. Last, but certainly not least, we delve into the profound world of supersymmetry. Unlike the other four symmetries that I talked about earlier in this video, supersymmetry remains unproven experimentally as of yet. Supersymmetry reveals a remarkable connection between particles in physics of different types. Supersymmetry posits that for every particle in this universe, there exists a partner particle. Or what physicists like to say, for every boson there is a fermion, and for every fermion there is a boson. This symmetry, if proven experimentally, would ultimately link the two classes of objects in physics, forces and matter. Forces show up as bosons in the universe, and matter shows up as fermions in the universe. With supersymmetry true, forces as bosons will have a partner fermions as matter, and hence forces and matters would be linked. Supersymmetry holds the potential to revolutionize our understanding of the universe. It may also help us bridge the gap between gravity and quantum mechanics. We would discuss more about this elusive but special symmetry of nature in a dedicated video later. And that concludes our exploration of the symmetries in physics. From translational symmetry to supersymmetry, these concepts provide us profound insights into the structure and the freedoms that physics gives us to view our universe. Thank you for joining me on this captivating journey. I hope you enjoyed this video on symmetries in physics that help us and free us to observe the fabric of our reality. Don't forget to like, share, and subscribe, and hit the notification bell button for more similar content. Also, in your comments, do let me know which other symmetries of nature excite or surprise you. Until next time, signing off, your host, Madhur. Keep exploring and stay curious.